Good. Yeah. So we were looking at indices the last day we met. Um, and I remember kind of summarizing. Let me chop the whole bit here. I remember anybody remember the laws that I give? Laws of indices, right? This is a summary of them again, right? So what we're gonna do, we're gonna apply them to, do basic algebraic manipulation, simplifying stuff. We're going to even attempt solving simple equations where the unknown is in the index, right? And that will lead straight on to something called logarithms, which we'll do later in the evening, right? So let's start with applying these laws to basic stuff. I remember when we were doing um, adding, subtracting, multiplying, and dividing algebraic expressions. I remember let's say you had something like this, and you had to simplify. Let's say, all right, p to the fifth, p to the fifth, multiply by um, let's say q. All right, I should go with pq to the third. All right, p2 p to the second power, q to the, all right, fourth power. Let's say you have to do something like this. And we used to do this. We used to write out p by p by p by p, write out the whole thing and then, put all the p's together, put all the q's together, and then simplify, right? I hope you remember those days. So we're not going to do that now that we have the laws, right? Now that we have the laws, you want to see this as, all right, you don't have to write it back like this. That's equal to p to the fifth power multiplied by p to the second power multiplied by q to the third power multiplied by q to the fourth power. And according to this law here, right, that's this one here, you add the indices of the one with the common base, right? So you have p here and you have p here, so we can add this. And you have p to the seventh power, and you add the powers on the q, and you get q to the seventh power, right? And you can even do this for, you can say this is pq to the seventh power, right? Using, and again, this one, you're using this one here, right? No need to write out the thing, expand the thing to simplify it anymore. We use the laws of indices, right? Same thing with division. If I were to, anybody is making a note or so,
Yes.
you're not
Yes,
rushing.
sir.
Yeah, take your time.
Sir, would you be having another test?
Yes, there has to be a test too, right? Somewhere in the course outline, said it. We'll have it soon. Today is what, the 25th. We'll talk about it at the end of the class. I have to go and look at how many topics and so we have covered. We'll speak about it. Don't worry. Remind me at the end, right? Good. So uh, get rid of all of this. Similarly, if you had to do the division, okay, let's go with, um, let's say you have p to the fifth power, q to the seventh power, divided by what's it? P to the third power, Q to the second power, right? You simply subtract the indices, right? And that will be what? 5 minus 3 is P squared. 7 minus 2 is 5, Q to the fifth power, right? No need to expand the whole thing and cancel powers and all of that. You just subtract. Let's do a few more. So let's say you have, I'll use some ugly numbers now. Let's say you have, all right, you have to simplify x to the 1/6 cube times x, x to the, or let me go with it, yeah, uglier one here, right? This is taken from the notes that we had earlier, right? I think I have it in the in Moodle. Good. So this here, using the laws now. So this one here, we can simplify using this here, right? And you end up with x to the 3/6 times, okay, this one here now, we can use here, right? This here, right? You can use that there. So we end up with x to the 5/2, right? There's a square root here, even though we don't have to write 2 in here, right? We know it's a square root. If it's a cube root, we write 3, right? If it's a fourth root, you write 4, but when it's a square root, you don't put anything. And now we can add these two up, right? So this is equal to x, and you're going with this force rule back now, right? And you add, so 3/6, well, that's half, right? Half plus 5/2, which is equals to, what's this? 2.5, and half is x to the third power. So we're making use of the different laws. Good, I can remove this.
Excuse me, sir.
Uh,
Can you explain what
Sure.
you're about?
Okay, yeah. So I don't know if the arrows are confusing you, right? I hope the arrows aren't. I'm saying to simplify this here. To simplify this, you see me circling it? X to the 1/6 to the third power. I'm using this law here. Notice I'm tracing here. I'm using this law, which means you multiply the power inside the bracket by the power outside. That's what you get. So you multiply 1/6 by 3, you get 3/6, right? Good. Then the square root of x to the 5, I'm using this law here. This law. notice that when you have the nth root of a to the m power, it's equal to a to the m over n. That's what's happening here. X to the fifth power, the square root of x to the fifth power is the same as x to the 5 over 2 power. That's what you have here. And now you have the product of two x's, right? So raise to some power. So we go into this force law. Going to this force law. Oh my. All right, yeah. And we add the indices now, right? Because the force law says if you are multiplying two expressions, they have a common base, you can add the powers, and that's what we're doing here. 3 over 6 is half, right? And 5 over 2. You add half plus 5. 5 over 2 is 2.5. 2.5 plus half is 3. So you end up with x to the third power. Very simple stuff, man. Very, very simple stuff. You're going to reach the real stuff just now when you do logarithms.
Okay,
That is
sir.
when you're doing, that is when you're doing the hardest stuff. Let's take another one. Let's go ahead. All right. 3x to the minus 1/3, y to the 1/3. Oh, that's not 1/3, to the minus 3 times 2x squared y to the 2/3, right? So everything is multiplying here. So you just add the indices, right? You add the indices of the ones with a common base. You add the indices on the x's and you add the indices on the y's. And of course, this 3 by the 2 you multiply. So you get 6x to the minus 3 plus 2 y to the 1/3 plus 2/3, right? So you end up with 6. All right, this will become x to the minus 1 y to the, well, y to the fourth power, right? Good. Now this negative power here, right? Look here, look at this law, right? A to the minus m is equals to 1 over a to the m, right? So this now becomes 6y, put the y in the numerator, over, well, you don't have to put x to the 1 power. So the x to the minus 1 is the same as 1 over x. That's what we say. X to the minus 1 is the same as that, right?
Sir, can you go over back how you ended up with y only?
Y to the powers on the y is 1/3 and 2/3. 1/3 and 2/3 is 1. So you end up with y to the 1. You don't write y to the 1 power. You usually just put y.
Okay, sir.
Same thing with this x to the minus 1. This x to the minus 1 means you have to put the x in the denominator. But you don't normally write x to the 1 power, right? We understand that x means x to the 1 power. Some of these things, when you watch them at first glance, you don't get them. But that's what mathematics is about, right? It's about developing your cognitive processes. You have to spend time with it, decipher things, right? Don't feel if you don't understand something, no, you will never understand it. Lots of things we don't understand now, but in time we do. Some things we never understand for life, like some of our wives, right? Or some of you, your husbands. You live with a man 10 years, you want to know, I can't understand you, wife. Or you can't understand you, woman. At least maths, you spend about 2 or 3 minutes and you get most of it. So some of the things you have to take some time and decipher. What is this? What is this? Take some time. And that's why I also advise, and I'm happy that some people are slowing me up and say, look, I'm taking notes. Note taking is important, right? Lots of times if I give you this video, which I will give you the video, what happens, you don't have the time to look it through. If you start it, you get bored, you're not paying attention as because look, this thing hard to follow, and you skip out pieces, you don't see it to the end. That's why the YouTube people, they normally say, watch the video to the end and there's something special there. Most of the time it's not true. They just want you to watch it to the end because they get paid for every hour that you watch videos, right? So most of you don't watch the thing to the end. I have a way of a video don't capture me for the first 10 seconds, later with it. So it's good to do some note taking. Good. Let's simplify another one. Yeah. Okay, let's use some actual numbers. Uh, let's say you have to evaluate, right? What is that? Evaluate 2 to the minus 1/3. What's that? Under this law here, it's equals to 1 over 2 to the third power, which is 1 over 8, right? Simple enough, right? So take another one, you get 3 squared to the minus 1/3, no, minus 3, right? What is that? That's equal to 1 over 3 squared to the third power, right? Which is equals to 1 over 3 to the fifth power, right? That's some big horrible number at the bottom there now. 729 they have here. Let's take another one. Let's go with, all right, 27 to the minus 1/3. Right? Not all of them will be easy to guess, right? So you want to think of 27 as 3 to the third power, right? 27, you want to see it as 3 to the third power, which is equals to, well, this 3 by that 1/3, you get 3 to the minus 1, right? The minus 1 comes from multiplying 3 by minus 1/3, which is 1 over 3. Follow that one? Tricky? And I can go on and on and on, you know, there are infinite amount of things you might want to simplify using indices. I can't show you all of them, right? You have to practice. Let's do another one. Okay, 125 to the minus 2/3, right? Again, you want to see 125 as what? 5 cubed. So you have what? 3 by minus 2/3 will give you minus 2. This now turns out to be 1 over 5 squared, which is 1 over 25. Follow that one? Let's do a hard issue. 81 over 16 to the minus 3/4. Right? So that's going to be 81 to the minus 3/4 over 16 to the minus 3/4. Right? So this basically is this. It's like this here is supposed to be 1 over 81 to the 3/4 divided by, right? Divided by, again, this here can be written as 1 over 16 to the 3/4, right? So, you know, you do the flipping and so you 1 over 81 to the 3/4 multiplied by 16 to the 3/4, right? And that becomes 16 to the 3/4 over 81 to the 3/4, right? And then 16 you want to see as what? 16 is 2 to the 4th power. And this one is what? 3? 3 to the 4th power as well. 81, right? So you end up with, okay, this 4 and that 4 cancel. You'll end up with 2 to the 3rd power over 3 to the 3rd power, which is equals to 8 over 27. And that's the kind of thing you see, you know? Good. So as I said, you can, all kinds of things can be out there where you have to use the laws to simplify them, right? Now, what about if you have an equation? You have an equation where the unknown is in the index. Let's see if I can get you one. So, all right, you're asked to solve something. Solve 64x equal to 16. Right, what do you do here? Well, 64 and 16 both seem to be, you can write them as a power of 2, right? So 64 will be what? 2 to the 3rd, 4th, 5th, 6th? Is it the 6th power? 2 to the 6th power, 64. and 16 is 2 to the 4th power. See if that's right. So this can be simplified to be 2 to the 6x equal to 2 to the 4th power, right? If the base is the same, then the power's got to be the same. Then 6x, right? So this implies that 6x equals 4. X then is equals to 4 over 6, which is 2/3. How are we doing with this? Easy to understand? Hmm? Not hearing any feedback.
Yes, sir. We message in the chat.
Well, how am I going to read messages and unmute and talk to me, man? So you see how we going dong.
Yes.
We used to get a face-to-face class, right? Now we get an online class and people still texting me in the chat. How I gonna read the chat and talk to you? So y'all want to talk to me, they're online, you're not talking to me.
Trying to process it, sir. We're trying to process it.
Soon what we gonna do, we gonna start to we gonna communicate telepathically. Yeah, I gotta read you mine, you gotta read me mine. Right? When you're
Well, that,
silent, I just move on. When you're
well, then we'll
protest,
be
I
in a
slow
dangerous
down.
position.
Yeah,
Because
right?
Sir,
there's no
wanna
telling
read
what's
we
going
mind.
to our mind. I tell you, you won't want to read it at all. You may not be able to answer it tonight.
No, most of the time it's oh God, man. Sir, put the whole class to sleep or what?
Right.
Alright.
You
And I
won't put the
bet you
class to sleep.
majority the whole class is
You put the
saying.
class to and think deep.
Okay.
Put the class to and think real deep.
Okay, good. Look at this one. So you can see that maybe, okay, 81 can be written in terms of 9 too. So 9 to the 2x equal 1 over 9 square, right? Using this law here, this one here, I can now write this as 9 to the 2x equal 9 to the minus 2. So that implies, right? I'll put it here, implies that 2x equal minus 2, x then equal minus 2 over 2, x equal minus 1. Right, so that's a little bit there on when you have to solve an equation and the power is in the index. What did I say? Not the unknown is in the index. Did I say the power is in the index? I mean the unknown is in the index or the power. Good. So let me pose a question. So if you have a situation like this now, and that will lead straight into what we call logarithm. Like if I have 2 to the x equal 10. So I ask you to solve this. Now there's no way, I mean, not no way. It's not simple to write 10 with a base of 2 and something up here. It's not easy. It can be done, but it's not easy. It's very difficult. And that brings us to now something called logarithms that can help us to do that. So what we can do, we can take a short break. We come back at 6:25, right?
Okay,
And
sir.
we're going to take on logarithm.
Okay, sir.
Good. So as I said before, we
Yes,
can be
sir.
able to solve an equation of this sort. We have to know about something called logarithm, right? Logarithm. Good. So what's logarithms really? Well, it's just another way of expressing the power that a number has to be raised to give another number. So let's take the example. If you have, all right, 2 to the third power equal 8. We're familiar with this notation, right? Because this is 2 raised to the power 3 gives you 8. We know that. Now we can write this a different way. This is what we'll see. The logarithm of 8 with a base of 2 equals to 3. Right? So it's like saying the same thing, but in a kind of inverted way. Right? So the logarithm of 8 with a base of 2 is equals to 3. Right? So you're saying the same thing. You're saying that if you raise 2 to the third power, you will get 8. But you're just saying it a little differently. All right, some more examples. Let's say, all right, the logarithm of 9 with a base of 3 is equals to 2, right? Which is the same thing as saying 3 to the second power equal 9. All right, let's take a third one. Let's say you have, all right, 1/5 to the minus 2 power equal 25, where we can write that as the logarithm of 25 with a base of 1/5 is equals to -2. Right, so simply put, let me write that generally. Let me see if you can, I'll cut it from this. Yeah. Right, so the logarithm of b with a base of a equals c implies that a raised to the c power will equal to b, or b is equals to a raised to the c power. That's what logarithms is about. All right, just to do a few more examples, let's say you want to express in logarithmic form, right? And you have something like, all right, 10 to the minus 2 equal to 0.01? Well, it means the logarithm of 0.01 with a base of 10 is equals to -2. All right. Alternatively, if you have, all right, you want to express something, express in index form, right? And you have something like this. The logarithm of 625 with a base of 5 equal to 4. Well, it means that 5 to the 4th power equal 625. Think you're getting the knack of it?
Yeah.
Yes, sir.
Good. So one of the things, all right, let me go into the laws first, and then let me fetch the laws for you over. Just like how you have the laws of indices, right? You have the laws of logarithm, right? So the logarithm of if you have the sum of two logarithms, right? It's equal to the logarithm of the product of x and y. So here you have the logarithm of x plus the logarithm of y. Notice we're using a common base. Some textbook, when they give you the laws, they wouldn't put a base. They expect you to understand that the base has to be common, right? The base has to be common. Yeah. So the logarithm of x plus the logarithm of y is identical to the logarithm of the product of those two numbers, right? And you can verify that. I don't have to, like, okay, the logarithm of, let's say, all right, 100 with a base of 10 is 2. The logarithm of, let's say, 10 with a base of 10 is 1, right? So that should mean that the logarithm of, well, okay, the sum of these two, right? The sum of these two is 3. So the logarithm of the product of 110 will give you 1,000, right? So the logarithm of 1,000 with a base of 10 is 3. You see? So it's true for that first law. And same thing if you were to try numbers here, you will see that it's true. The logarithm of x minus the logarithm of y is equivalent to the logarithm of x divided by y. Right? The logarithm of x raised to the power y, right, is equal to y multiplied by the logarithm of x. Right? So just to illustrate, with a few examples. I wanted a few examples from Ori. Okay, let's take the logarithm of um, let's say a square, b square. No, let me not use the same number. Let me take out the power. I won't go that far so quickly. The logarithm of AB, if you were to expand that out, is equal to the logarithm of A plus the logarithm of B, right? And no need to put a base here, right? If you want to use X, no problem. We know that we're dealing with a common base, right? Let's get a little more complicated. Let's say you have the logarithm of A squared over B. Let's say go with B cubed. That will be equal to the logarithm of A squared minus the logarithm of B cubed. And then we can apply this third law here. Bring the 2 to the front, bring the 3 to the front, and you get 2 log A minus 3 log B, right? Notice I'm not using a base. I'm assuming that the base is the same. Good. So now that we're introduced to the laws of logarithm, and we're going to use them a lot, right? The trouble with logarithms is that you can't have the logarithms of numbers with all kinds of bases, right? What I mean by that, okay, mathematicians realize that, you know what, we can't work with any base, right? We can't have logarithms in all the bases in the whole wide world. So what they did, they decided, look, let's choose a base to be the standard. And you can guess what is the base that they use as the standard. Base 10, right? Base 10. In other words, they actually, long years ago, they developed tables, what you call 3-figure and 4-figure tables, where every number, right, is written. Well, as a matter of fact, I'm talking about positive numbers, right? Not negative numbers. All positive numbers were written in terms of a base of 10, right? So you can actually, and as a matter of fact, not well, with the advent of calculators, they actually wrote code and they made calculators that can actually calculate the logarithm of any positive number with a base of 10. Like if you have your calculator, you look, your calculator should have LG somewhere. Do you see this? LG or LOG? And you can type in the logarithm of 3. You can type in the logarithm of 4. You can type in the logarithm of, oh, as I said, most calculators will have LG, some would have LOG. What does your calculator have? The logarithm of 20, 120, 1200. The calculator will give you that. Can you check your calculator? See what you have.
LOG, sir.
You got LOG, okay. I had one here, Texas Instrument, that had LG, common LG, right? And oftentimes when you see LG, you know that, oh, you're dealing with base 10, right? And this is what they call common logarithms. Common logarithms, right? Common logarithms. Because mathematicians sat down and calculated by hand, you know. Those times they had computer. And they make up what you call 3-figure and 4-figure tables. If you're all like me, when we wrote CXC, right? A couple of years before me, people didn't have calculators, right? This scientific calculator you're talking about. They used to allow you to use like an adding machine, if you have one. If not, you had to do everything by hand. And to help you with logarithms, they used to give you a what you call a 3-figure and 4-figure table, right? And that is what you would read off the logarithms of numbers with and do your calculation. Of course, with the advent of scientific calculators, you were able to find the logarithm of any number now. Not any number, any positive number, right? If you were to look at a graph of the logarithm of a number, it will look like that, right? So a number raised to some power would look like that. I should curve it up some more. And the logarithm, the log of x, looks like this. So you can't have, if you check this, check log of -1. Tell me what the calculator says. What does it say? Nobody trying it? Logarithm of -1?
Sir, mind giving me error?
Error, yes. And I showed you the reason. The logarithm, the logarithmic function, let me erase this part. The logarithmic function looks like this. So you don't have the negative x-axis in a function then, meaning you can't feed in a negative number. The logarithm of a negative number does not exist, right? So there you can't find the common logarithms of a negative number. Later on, when they found out a number e. Do you see this number on your calculator, e? You seeing that number, e, on your calculator?
Yes, sir.
What is it equal to?
2.71.
2.71828 and so, right?
Yeah,
It's
go
a
on.
number very much like pi.
Yes,
We
sir.
don't have an exact number for it. So they discovered that the number e is naturally occurring, in nature. So they came up with something called, well, they use e as the base. So just like how they were using 10 as the base, and they came up with what we call natural logarithm. Sorry, not natural. Common logarithm. And they used 10 as the base. Well, because they saw e occurring naturally in nature, they came up with, or they use e as the base of logarithms as well. And they call it natural logarithm, right? Natural logarithm. Some books would use the word Neperian. There's an R here. Neperian logarithm, right? And you will see on your calculator the ln, ln. Do you see this on your calculator? The ln of 10, the ln of 20. Again, you can't have the ln of a negative number, right? -5. You can check it out. So ln or ln, you see on your calculator there. So instead of log, you have ln. So a lot of calculators now, you don't see 3-figure and 4-figure tables with ln in them. But the calculators that have been recently developed would have the Neperian logarithm or the natural logarithm, ln. right? So you can find the ln of any number, positive number that is, right? Because ln of negative numbers don't exist. You'll see your calculator will return an error. So now we have two possible logarithms that we can work with. The common logarithm, base 10, and the Neperian or the natural logarithm, where the base is e. Right? And as a matter of fact, anything that you have now, right? Any other base that you have, you can actually change the base to ln or log. And let me give you the formula, right? If you want to change, all right, if you have a logarithm written, right, the logarithm of a number c and the base is a, but you want to change it to b. You don't want a, you want b. Well, you simply do this, right? Use this formula. The logarithm of c with a base of b, the new base, over the logarithm of a with a base of b. Right? So this formula helps you to change the base of a logarithm. So if you have, man, the logarithm, all right, logarithm of, let's say 25 with a base of 5. You know that to be 2, right? But then let's say you have the logarithm of 30 with a base of 5. You can't pick this out. You can't pick that out. You say, oh my, how am I going to calculate that now? So what we do, we can change the base from 5 to either 10 or e, right? So, okay, the logarithm of 30 with a base of 5 is equals to, let's go with ln. The ln of 30 over the ln of 5. Right? So we might not be able to calculate this directly, but we can change the base from 5 to e, right? And you're going to use ln. Ln is another way of saying logarithm with a base of e, right? That is what that means. But we don't write it logarithm with a base of e. No, we don't write it like that. We put ln. You can also do it with base 10. The logarithm, and you can check it. You can check it with your calculator. The logarithm of 30, the base of 5 is equals to, and we're not going to put 10, we're going to put LG, logarithm of 30 over the logarithm of 5. And when you punch this in your calculator, don't sit down there passively. Punch this and you'll see that this, whatever that is the same thing here, regardless of which base you use. Check it and see. Some of you use ln, some of you use log. And see if you get the
Sir, the logarithm for 30 is 3.4011.
well, you divide it. You got to divide it by ln 5 now. Do the division completely.
.1132. May divide it.
Okay. So you get what? 2.1.
1.
All right, go with 2.1. Anybody trying log? See if you get the same thing.
Yes,
Use
sir.
the calculator on your phone.
Good. So you get 2.1 as well. And what you could do, try now with 5. 5 raised to the 2.1 power. Can your calculator do that? See if you'll get roughly 30.
Pardon me, sir?
Raise 5 to the 2.1 power and see if you will get 30. You should get near 30, 29 point something. Your calculator can do that. Raise 5 to the 2.1 power. Can you do that?
Sir, I don't know how to do the raising part.
Well, you gotta learn your calculator. Right? Because remember we were trying to evaluate the logarithm of 30 with a base of 5. And we found that to be 2.1. So 5 to the 2.1 should approximate to 30. It should be 29 point something, close to 30. Figure out how you can do this with your calculator, right? Good. So that brings us to, remember we had some questions like, what was it we had earlier? Let's see if I can go back. When we were doing, okay, look at this one. 2 to the x equal 10. Let's see. All right, let's go back now. See. So we have to solve an equation of that sort, right? We have to solve 2 to the x equal 10, right? So what we could do, log both sides. Log of 2 to the x equal to log of 10, right? The law says you can bring this x to the front. So you get x log 2 equal to log 10. X then is equal to log 10 over log 2. And that should give you an answer here, right? Check and see. Log 10 over log 2.
Um, 3.32, sir.
3.32, all right. And check. 2 to the 3.32 should give you 10, or near 10, approximately 10. Right? So you see how logarithms can be used now to solve. Why I was able to do this is like this here can be written like this. The logarithm of 10 with a base of 2 is equals to x. That's all. So using the change of base formula, you don't want 2 because you don't have a calculator that will work in 2. Right? So logarithm of 2 with a base, of 10 with a base of 2 is the same as, let's say you use log 10 over log 2. Isn't that the same thing here? Same thing here, right? Which is 3.32. You don't have to use log. You can use ln too. You can use ln, right? From here,
Use limit to get the same answer.
yes, ln 10 over ln 2 should be 3.32.
Yes, sir. It's the same thing.
Yeah, you gotta get the same thing. Let's do a harder example. Look at this one. Let's say you have to solve this equation. Solve 2 to the 2x plus 3 bracket 2 to the x minus 4 equals 0. Right? So you can watch this and see that this is 2 to the x squared plus 3 to the 2x minus 4 equals 0. See if you follow that. So I took this power here and split it up like this. The reason why I want 2x to be common here and here. 2 to the x, right? Not 2x. 2 to the x common. So what I'll do now, I'll let y, big Y, be equal to 2 to the x, right? So this equation becomes y squared plus 3y minus 4 equals 0. Right? This here I can factorize now. Y plus 4 times y minus 1 equals 0. Right? That implies, I'm going up here now, that y equal minus 4 or y equal 1. Right? In other words, remember y is 2 to the x. So 2 to the x equal to minus 4 or 2 to the x equal to 1. Right? So you would know that 2 to the x cannot be minus 4. The reason why is the graph 2 to the x is a curve like this. Right? It's a curve like that. It doesn't go over to the negative side. It doesn't go over. So there are no real solutions. No real solutions. Solutions for 2 to the x equal minus 4, right? On the other hand, though, this one over here, 2 to the x equal 1, you know that 1 is the same as 2 to the 0, right? 2 to the 0 is equal to 1. As a matter of fact, any non-zero number raised to the power 0 is 1. Right? That came out in laws of indices. Maybe I didn't highlight it well enough. Therefore, x equals 0. And that's your solution. Think you get this? And logarithmic equations can get far more complex than this, right? It's just an awakening to you. Right? Maybe let me do one or two more. Let's say I have, okay, you have to solve 3 to the x equals 6. Right? You log both sides or you ln both sides. Let's go with ln. Ln of 3 to the x equal to the ln of 6. Bring this x to the front because the laws, there's a law that says you can do that. X ln 3 equal to ln 6. X then is equals to ln 6 over ln 3, and your calculator will give you that. I don't want to get into harder logarithmic equations, right? Because they can get very, very hard. I'm going to stick with this for now. The simple things. Good. So I think we've done a nice intro to logarithms there. So as I said, I'm not going to get into the harder stuff. And we can probably stop there, right?